Go ahead and start it. In today's lecture, we are going to talk about steel in chapter 3. Steel is one of the important construction material that we are using in civil engineering. So today we are going to talk about steel, how the steel is going to be manufactured, how we are going to use the steel. So as a background, steel is the third most used construction materials after the concrete and the asphalt. So the most used construction material is concrete. Then the second most used construction material is asphalt, concrete, and finally we have the steel. So the use of iron dates back to about 1500 BC. So people know how to use steel from a very old age. And the first metals, when we say first metals, those metals that are primarily composed of iron. So when we say first metals, it means the primary component is iron. The first metals were produced on relatively small scale until the blast furnace was developed in the 18th century. So before the 18th century, the iron production was small. No, it was not being produced on large scale until the invention of the blast furnace. So here is a blast furnace, just like a big furnace with a special equipment. So after the invention of the blast furnace, the production of the steel has been produced on large scale. So steel production started in the mid 1800s. In the second half of the 19th century, steel technology advanced rapidly due to the development of the basic oxygen furnace. So again, after the invention of the blast furnace, we have another type of furnace, oxygen furnace. This one used in order to reduce the amount of the carbon in the steel and also in order to remove the impurities. So also this one help the production of the concrete, and also we have the continuous casting method, which means that after we got the steel directly, we are going to produce the materials from the steel. And nowadays, more recently, computer control manufacturing has increased the efficiency and reduced the cost of the steel production. So in order to sum up all of this, we know the steel from very old age, but with the invention of the blast furnace, that increased the scale on which we produce steel. Then the process became quicker with the oxygen furnace and the continuous casting method. And nowadays we are using computer, which increase the efficiency of the production of the iron. So we need to compare the small comparison between the steel and the asphalt and concrete. So as engineers, we directly influence the strength, stability, and durability of the concrete, asphalt, aggregate, and soil, right? So as engineers, we can influence the strength and the stability and durability like we have studied about the asphalt and the concrete. But we cannot do that for the steel. Of course, only in rare cases, but generally speaking, we will not be able to directly influence the strength, stability, and durability of the steel. So who is going to control all of this? Steel properties are dictated by the manufacturer. So the manufacturer who is going to set the terms, not you as an engineer. So even though as civil engineers, we do not specify steel properties or shapes, of course, except in rare application, we still need to understand how steel is produced. Even though we are not going to set the terms in order to produce the steel, but it's important for us to understand how the steel is produced. So we have different type of steel in construction. We use a different type of steel. We have structural steels like the blades. The blades, this is the blade here. It could be used for floors and so on. We have the bars like this one. We have the pipes, and we have many structural shape. Also, we have the cold form steel like the studs. This one here called this studs, like the truss and like the roofing and the cladding. Also, we have fastening. We have the fastening products like the bolts, nuts, and the washers. We have the bolt, we have nut, and we have washer. Also, we have the reinforcing steel, the steel that is going to use for the concrete in order to strengthening the tension capacity. Also, we have miscellaneous like the forms, plans, and hardware. Okay, so we have different type of steel in construction. So why we should use the steel? What is the advantages of the steel? First, we have the strength and the stiffness. The steel members have a higher strength per unit weight ratio. So if you are going to compare the steel with concrete and with asphalt, and you are going to determine this ratio, the strength per unit weight, then you are going to have you are going to get that the steel has a higher strength per unit ratio. Even though the steel has a higher unit weight than concrete, the unit weight of the steel is larger than the concrete, its effectiveness is much higher. This means that the steel members and the frame system are generally lighter than the concrete structure. So if you have a frame that made from steel and another frame made from concrete, then the frame that made with the steel is going to be lighter than the frame that which made from the concrete. Also, we have the uniformity and permanence. So steel properties do not change appreciably with the time. Remember, regarding the concrete, we talk about the creep, about the shrinkage. With the time, we're going to have many problems. So all of these problems like the creep and the shrink does not exist in steel. So the properties of the steel is not going to change with the time. Okay, and also if you are going to maintain the steel in a good condition, a steel structure can last almost indefinitely. So for the steel, it can last forever if you provide good maintenance. Okay, if you provide good maintenance, the steel can last for a very long time. Also, we have other proper advantages for the steel, like the ductility and the toughness. The steel has a remarkable ability to withstand the large inelastic deformation, which means that it has large ductility. We talk about the ductile material and brittle material. And the steel is going to provide a large capacity of ductility. Also, is going to provide a large amount of energy. The toughness. Remember the toughness. We managed to determine the toughness. If you have a stress strain diagram, you could be able to determine the stiffness, the toughness. So the toughness of the steel is large. That is going to help us, especially in seismic regions. So these qualities, the ductility and the toughness, make a steel a great choice for both general structural needs as well as in seismic regions when you are going to expect to have earthquake. So the ductility and the toughness is a good advantages when you're using steel. Finally, we have the sustainability. Structural steel produced in the US contains 93.3% recycled steel scrap. So steel, it could be recycled on large scale. Okay. So at the end of the life of a given building, 98% of the steel is recyclable. So if you made a building from the steel, then 98% of all of this steel, it could be, you can recycle that amount. Okay. And this could be done with no loss of its physical properties. So you can recycle the steel without using the physical properties. So in terms of sustainability, using steel is very good. So now we need to talk about how to produce steel. We are going to talk about the production of the steel. Generally, we have three steps in order to produce steel. We have three steps. Step number one, the reduction of the iron ore to pig iron. In this one here, it's going to be completed by heating the iron ore. Here is the iron ore. Iron ore is the rocks and minerals from which metallic iron can be economically extracted. The ores are usually rich in iron oxides. So we are going to first pick up this kind of rocks. We call this iron ores, this kind of rocks rich in iron oxides. So we need to pick up this one here, and we need to put this in the blast furnace. This one in the blast furnace. I need to put the iron ore, and also I need to use the limestone. I need to use the coke. Okay, so I need to have the iron ore. I need to have the coke, and I need to have the limestone. So the coke is the solid fuel with a few impurities and high carbon content, usually made from coal. So I need to have coke, and I need to have limestone, and I need to have the iron ore. So what is the purpose of the coke? The coke is going to provide carbon to reduce iron ore in the ore. So here we have the ore. The ore is going to be rich in iron oxide. So the coke is going to provide carbon to reduce the iron ore in the ore here. Also, we have the limestone. The limestone is going to help us to remove the impurities from the iron ore. So the basic component is the iron ore, but I need to use the coke in order to provide carbon to reduce iron oxide. And also I need to use limestone in order to remove the impurities from the iron ore. So the first step here, I'm going to use a blast furnace. I'm going to have iron ore. I'm going to have limestone. I'm going to have coke. Okay, so all of this is going to be delivered to the blast furnace with a certain amounts. Okay, so we've done with the first step. Then the process from step number one, we are going to have the pig iron. So the result of mixing the iron ore and the coke and the limestone, we are going to get the pig iron. So the ordinary pig iron are produced by the blast furnace. So from the blast furnace here, the molten iron here is the pig iron. So what is the properties of the pig iron? This one is going to have between 90 to 94% iron. We are going to have 4% carbon, but this percentage here is way too high for structural steel. It could be used for cast iron. Usually the cast iron, we made the machines and so on from the cast iron, while the structural steel is the steel that should be used in the structural purposes. The cast iron, like the pumps, like the pipes, and like motors. In those, we are going to use cast iron. And the percentage of the silicon between 1/4 to 3.5%, and the phosphorus between 0.03 to 1%, and the silver is less than 0.1%. So here is the properties of the pig iron. The problem with the carbon, we need to reduce the percentage of the carbon if we are going to produce structural steel. So in this step should be completed by removing excess carbon and other impurities. So in this step, I'm going to remove the excess amount of carbon, and also I'm going to remove any impurities. So the excess carbon along with the other impurities must be removed to produce high quality steel. So in order to produce high quality steel, you need to remove the excess carbon, and also you need to remove the impurities. And the same process, it could be used for scrap in order to for the steel to be recycled. Okay, scrap is the remaining of the steel. So the same process, it could be used for scrap for recycling processes. So we have two type of furnaces are used for refining pig iron to steel, either to use the basic oxygen or to use the electric arc. In both method, we are going to remove the excess carbon. In the basic oxygen, we are going to remove excess carbon by reacting the carbon with the oxygen to form gases. While in electric arc, we are going to use an electric arc between the carbon electrodes to melt and refine the steel. You can use this one and that one. But the primary goal for this step, reduction of the carbon and the control of the phosphorus, silicon, silver, and magnesium. So the last step, step number 3, regardless of the refining process, whether you are going to use the basic oxygen or electric arc in order to remove the excess carbon and the impurities, the molten steel with the desired chemical composition is then either cast into ingots, which is a large block of steel. Then we are going to put the steel like that in a large blocks, or it can cast continuously into desired shape. So once I got the molten steel, I have two options: either to put them as ingots in a large block, or I'm going to directly cast the steel in desired shape using the continuous casting. So I'm going to place the concrete to go through this process of rolling so that we can shape the concrete into the desired shape. So now continuous casting, this one is a continuous casting. I'm going to produce directly, I'm going to produce steel in desired shape using the continuous casting. So the continuous casting with hot rolling is becoming the standard production method. So nowadays, no one is going to put the steel in ingots. Okay, the standard now, we are going to directly produce the steel in desired shape using the continuous casting and the hot rolling. Why we do that? Because it's more energy efficient than cast ingots. Because like you can see here in the ingots, I need, in order to get my desired shape, I'm going to reheat the ingots again so that I can get my desired shape. So this one is going to consume more energy than the continuous casting. Here we have a graph that can summarize the process. First, I need to have iron ore, and also I need to have coke, and I need to have limestone. So I'm going to put them in the blast furnace. Okay, then I'm going to have the molten steel, the hot metal. Okay, so now I'm done with step number 1. I'm going to have the pig iron, which is rich in carbon, and also you have some impurities. In order to get rid of the excess carbon and the impurities, either to use the basic oxygen furnace or the electric arc furnace. Okay, the same step here. If you have scrap, if you have remaining of steel, you are going to use the basic oxygen furnace or the electric arc furnace. Like we just mentioned, regarding the scrap, we are going to use the same method. We are going to start from step number 2. So after that, we are steel in the desired composition. Then I have two options: either to use the continuous casting, this one, or I can put the steel in the ingots. If I'm going to put the steel in ingots, then later on I need to reheat the steel again, okay, so that I'm going to continue the rolling process. So here I'm going to use the continuous casting. I'm going to put the steel in shape like this one or this one, and like that one, and then it's going to go through the rolling. This one rolling is going to control the shape of the steel, and then I'm going to have the products, whether you are going to have rail, sheet pile, shape, bar, wire, rod, blades. All of this is the final products. Okay, so here I have the blast furnace, the first step. Then I'm going to have the second step, the basic oxygen furnace and electric arc furnace. Then I'm going to have the continuous casting. Then I'm going to have rolling process, and finally I'm going to have the main products. So now we have a good idea about how to produce the steel. We say that as civil engineers, we do not specify the properties of the steel. We do not specify the strength or the durability, but we need to understand the process. That is going to help us a lot. So now we need to talk about the iron carbon phase diagram. Okay, the percentage of the carbon is going to control the behavior of the steel. Okay, so if the percentage of the steel is more than 2%, the steel is going to be brittle. You are not going to have ductility. And also if the percentage of the carbon between 0.8 and 2%, again the steel is going to be brittle. If the percentage is more than 2, we are going to call the steel cast iron. If it's between 0.8% and 2%, we are going to call this high carbon steel, and also the behavior is brittle. And finally, we have the structural steel, which is we really want to use. The percentage of the carbon is going to be low, between 0.15% to 0.27%. And this one is the ductile. This one it have better ductility than the cast iron and high carbon steel. We call this iron carbon phase diagram. So the percentage of the carbon is going to control the behavior of the steel. Also, we have the alloy. We say the term alloy for a metal made by combining two or more metallic elements. So if you have a metal that it has been produced by combining two or more elements, we call steel is iron, have carbon. The carbon is going to show me the behavior, or it's going to control the behavior of the steel, whether you have cast iron or high carbon steel or structural steel. The behavior here is going to be different. But you need to remember that whatever the percentage of the carbon, the modulus of elasticity is the same for the all three, because they have the same atomic bonds. So I'm always asked about this. So please remember that whatever the percentage of the carbon, the modulus of elasticity is going to be the same. For example, here, I'm going to jump to this diagram so that you can understand this. So here we have steel, we have stress-strain relationship for steel with a different percentage of the carbon. So here I have this percentage, I have this percentage, and I have this percentage, and that percentage. So you can see here, when I'm going to reduce the percentage of the carbon, the behavior is going to be more ductile. If I'm going to increase the percentage of the carbon, the behavior is going to be more brittle, even though the strength is going to be better, but the ductility is going to be less. But here, if you are going to measure the slope, here the modulus of elasticity, the modulus of elasticity is going to be the same for all steel, whatever the percentage of the carbon. Okay, so you need to understand this point. So we have alloying agents. So we said that alloys are added to steel to alter the character of the steel. So here we have something similar to the admixtures in concrete. Here we have alloying agents. This is going to be added to steel so that we can change the character of the steel. They are 250,000 steel alloys. Only 200 is of interest to us. So by adding steel alloys, the steel properties could be changed. You could change the hardness, you could change the corrosion resistance, you could change the mechanability, you could change the ductility, and you can change the strength. So by adding the allowing agents, here we have example for that. If the percentage of the aluminum is less than 2, then you are going to, for example, remove oxygen in the steel melting. You can have 8 nitriding. You can restrict grain fourth. For example, if you have silver, if it's less than 0.05, then you can add mechanability. You can reduce the ductility, and so on. If you have nickel, copper, all of this is going to influence the behavior of this steel. This table is not for you to memorize, just to understand that you have allowing agents that can alter the behavior of the steel. Okay, so you can alter many properties like the hardness, corrosion resistance, mechanability, ductility, and the strength. Also, we have the cold form steel. Okay, so the cold form steel is produced from sheets of hot rolled steel. So when we say that cold form steel, this one is produced from hot rolling steel. So everything is going to be produced from hot rolling steel. So here we have the hot rolling steel. We could produce the cold form steel. Then we are going to store the cold form steel. Later on, we are not going to use heat, but we are going to use only these machines like this one in order to change the shape of these sheets. So no heat is required to form the shapes, unlike hot roll steel, and thus name cold form steel. So in order to get the final product for the cold form steel, we are going to use these machines like this one in order to change the shape of the steel sheets. So the cold form steel members and other products are thinner. These products thinner and lighter and easier to produce, and typically cost less than their hot roll counterparts. So this one is going to be shaped using no heat, using only these machines here, and the weight is lighter, and the thickness is thinner, and they are easy to produce. So the cold form steel is used for structural framing on the floor and on walls and on roof, as well as interior partitions and exterior curtains wall applications. The thickness of the cold form steel framing members range from 0.455 millimeter to 3 millimeter. So here we have the machines help us in order to produce the cold form steel. And this process here, the process of forming the steel using these machines, result in plastic deformation. You are going to have plastic deformation, and that is going to cause strain hardening. That is going to increase the yield strength, the tensile, and the strength are the hardness. But this one is going to reduce the ductility. So the steel is going to first is going to be flat, then is going to go through those rolling here, and then this one is going to be made to produce a desired shape. So the steel is going flat in the beginning, then is going to go through those rollers, and then the finished section is going to be like one of these. So here we have resulting cold form steel shape. The shape could be like that, or like that, or like that, or like that. So we have a special consideration for the cold form steel. You need to take care of the buckling because you have thin section, and also you need to take care of the corrosion, because this one, since the thickness is thin, is going to be susceptible to corrosion. So we need to take care of the buckling and the corrosion itself. So I'm going to stop here. Finally, we have a structural frame. So the cold form, like the cladding and the floor, is going to place here like this one for flooring or cladding, while the hot rolled structural shape like the beam and the column, is going to place here. So in order to come up with, or in order to construct a framing steel frame, you are going to have cold form steel, and you are going to have hot rolled steel. Okay, so it's very important to understand where to place the different type of structural about the mechanical properties and the chemical composition of the structural steel. When the structural steel is hot rolled, which means that we are going to produce shapes, plates, and bars. And all of this, you are going to use them in columns and beams and brackets, frames, and bridge girders. Okay, so the hot rolled structure shapes, plates, and bars, we are going to use them in columns and beams, for example. But the columns and the beams and all of this, they are graded. We have grades for them. And through the grading, we are going to know the mechanical properties and the chemical composition. So what do we expect in the mechanical properties? In the mechanical properties, we are going to know the yield strength. Remember, the value of the yield strength is the value in the material that differentiate between the elastic and the plastic behavior. And we have the tensile, or the ultimate strength, the maximum strength on the curve, and we have the percentage elongation, how much the steel has been elongated after the failure. And also we'll learn how to get all of this through the lab. In lab number 8, when we had the tensile test, we'll learn how to determine the yield strength, the tensile or the ultimate strength, or the percentage elongation. And also we have the chemical composition. Through in the chemical composition, we'll be able to know the percentage of the carbon. Now we know the role of the carbon in the behavior of the steel. And also we have other requirements because in the other requirement, limiting undesirable chemicals, we're going to provide desirable properties. So if you are going to limit some chemical, then you are going to improve the desired properties. So let's see an example on the grading of the structural steel. So according to ASTM designation, we have many grades here. The most used one is A36, but also we have A53 grade B, and we have A500, we have grade B and grade C. We have A501, we have A529, we have grade 50 and grade 55. So here, first we are going to look at the mechanical properties. We are going to know the value of Fy, the yield strength, the value of Fu, the ultimate strength, and the elongation, how much the element has been elongated after the so for example, look at A36. The value of Fy came out to be 36 KSI. So this one is the value of the yield strength, the point at which the behavior of the material is going to be plastic behavior, which means that after that value, we are going to have permanent deformation. Here we have the value of Fu, the ultimate strength. It has a range between 58 to 80. So this one is the maximum strength the material can withstand. And here we have the elongation. The elongation here is 23%, which means that the final length minus the initial length over the initial length is going to give me, as a percentage, is going to be 23%. Similarly here, we are gonna know, if you know the grade of the steel, then you will be able to know the value of Fy, Fu, and the elongation. Similarly, we are gonna do the same thing regarding the chemical composition. Again, if we are going to have A36, here the percentage of the carbon, is 0.26. Here we have the percentage of the copper. Here we have the percentage of the magnesium, phosphorus, and silicon. So here also we are going to know the value of the chemical composition. The value we talked about the importance of the percentage of the carbon, and those other minerals here, well, they are going to change some of the properties of the aggregate. They are going to act like alloying elements. So now we understand the importance of the grading. So we always buy steel in grade. So if you want to buy steel, you're going to say that I want steel of A36. I want this one here, for example. Then if you are not sure about who you are going to buy with, then you need to test you need to test the a sample of the steel to make sure that the values is going to meet the requirement. Also, we have different section shapes. We have I-beam, we have channel, we have wide flange, we have equal leg angle, we have unequal leg angle, we have T, we have sheet piling, we have rail. So also you need to specify the section, which section type of section that you want. Of course, this one is the cross section. Okay, so a section available through which you can choose whatever you want. Also, we have the structural fasteners. We use the structural fasteners in order to connect two parts of the steel. Okay, so this one like a connections. And we have the nuts. We have a picture for the nuts. We have washers. We have anchor rods. This one here. This one is going to be fixed on the ground. We have the threaded rods. This one here. This one also are going to connect two pieces of steel. And also we have the rivets. The rivets look like that, very old fashioned. Nowadays, it's rare to use the rivets because it's time consuming. The behavior is unpredictable and it's dangerous. Many workers get injured because of the rivets. This one like that. Okay, so also we use the steel as fasteners, nuts, washers, anchor rods, threaded rods, and rivets. Also, we use the steel for reinforcing. We know that the concrete is weak in tension. And actually, when we are going to design the concrete, we are going to ignore the tensile strength of the concrete because it's very small. And we need to put steel so that the steel is going to take the tensile stresses. Okay, so if you have a structural concrete member subjected to tensile and fractional stresses, we should reinforce the concrete with steel rebars. So the reinforcing steel or the rebar is manufactured in three forms. We have the plain bars, we have the deformed bars, and we have the wire fabrics. So let's talk about each and every one of them. We have the plain bars. Usually they are going to be round like this one here without surface deformation, which means that the surface is smooth like you can see here. So we have a problem with the smooth surface because the smooth surface, the bond between the concrete and the steel is going to be limited. They are not going to provide me good bond between them. And therefore, they are not typically used in section subjected to tension or bending. So we're not going to use this one if I'm going to have tension or bending because the bond is going to be weak between the concrete and the steel. And the bond between them is very important so that they are going to act like one element. The other one, the deformed bars, like this one here, they have protrusions or deformation. We have this one here on the surface. They are going to provide good bond between the bar and the concrete. Because of this deformation here, that is going to provide good bond between the rebar and the concrete. The deformed surface of the bar prevent slipping, so the steel bar is not going to be slipped, and that allowing the concrete and the steel to work as one unit. Like I just mentioned, they are going to work like a one unit because the bond between them is good. But if the surface is smooth like the plain bars, then the steel is going to slip from the concrete. Okay, so it's good to use deformed bars nowadays. We use the deformed bars more than the plain bars. So the deformed bars are used in concrete beams, slabs, columns, walls, footings, and pavements. In all these applications, we use the deformed bars. Also, we have the wire fabrics, look like that. The wire fabrics, they are flat sheets in which wires pass each other at right angle. So this one in X and in Y, the angle between them is 90 degree. So where we use the wire fabrics, we use the wire fabrics in concrete slab and pavement, mostly to resist temperature and shrinkage stresses. So this one is not going to be used in order to take care of the tension or the bending. This one mostly for resisting temperature because the temperature might rise or might fall, and that is going to cause a problem. So mainly we use the wire fabrics in order to resist temperature and shrinkage stresses. Also, we need to know the available bar sizes. Those reinforcing steel, they come into bar sizes. We have different bar sizes. So here we have bar number 3, 4, 5, 6, 7, 8, 9, 10, 11, 14, and 18. We have different bar sizes. Okay. For example, here, bar number 3, it has a diameter of 0.345 inch and the area is 0.1. So each and every bar number, it has its own diameter and its own area. And we have some properties regarding the bar sizes. So from number 3 to number 8, here from 3 to 8, you can determine the diameter if you know the number of the steel bar over the number 8. So for example, in bar number 4, if I want to know the diameter, I'm going to say that the number is 4. I'm going to divide it by 8, and then the diameter should be 0.5. So from number 3 to number 8, I can easily know the diameter using this formula. And regarding the bar number 9 here, in bar number 9, the area is 1. It's just special properties regarding the bars numbers. So this one is special number. The area is 1 in bar number 9. In bar number 10, the value of the diameter is the same as the value of the area, of course, numerically. Okay, because the area and the diameter, they represent a different parameter. But here, as a property, the value of the diameter numerically is the same as the value of the area regarding bar number 10. And also in bar number 11, this one here, the area here is equivalent to a square bar of 1.25 times 1.25. So it's just like you have a bar with a square cross section, 1.25 by 1.25. So if you multiply this value by that value, is going to give you this number here, 1.56. Also regarding steel bar number 14, the area is equivalent to square cross section of 1.5 times 1.5. Similarly, in number 19, the area is equivalent to square cross section of 2 times 2. So 2 times 2 is going to give me 4. Okay, this is just special properties. It's very important to understand them. Okay, this is going to help you in order to be familiar with the bar sizes. Also, we have the pre-stressed concrete. We use steel in pre-stressed concrete. The idea of the pre-stressed concrete, we know that If we have a beam, for example, like this one, if I'm going to apply a load, then the lower part is going to be subjected to tension, like we have seen in the lab, okay, regarding the flexural strength. We have done that test. So because this part here is going to be weak part because the concrete is weak in tension, then we need to put the steel reinforcement here so that the steel here is going to take care of the tension. The pre-stressed concrete, special type of the concrete, in that one, we are going to put cables or wires made from the steel. We are going to place it here, down there. Then we are going to apply a force, okay? Then we are going to close those gaps here at the end. We are going to apply a force, okay? And then we are going to close those gaps here. If you are going to do that, it's just like you apply compression at the bottom here. So if you are going to apply compression at the bottom, then the beam is going to curve like that, which means that here I have compression. I don't have tension anymore. Then when I'm going to apply the load again, then I have already a compression here. Then when you are going to apply tension, the compression is going to balance the tension so that at the end I'm not going to have any tensile stresses at the bottom. This is the idea of the pre-stressed concrete, or sometimes we call this the post-tension concrete. In order to do this process here, we represent the end of the beam. We need special wires, strands, cables, and bars. Look like that. So those types of the special wire, strands, cables, and the bar must have high strength and low relaxation properties. Okay, and they should be made of high carbon steels and high strength alloy steel. So this one should be made of high carbon steel. So here we don't want ductility, we want strength. So we are going to use high carbon steels, and also we are going to use alloying steel in order to enhance the strength more and more. Finally, we need to understand the test that should be on the structural steel. Of course, the most important one is the tension test. Also, we have that in the lab, the tension test. So the tension test, according to ASTM E8, should be done according to that standard. The tension test on steel is performed to determine the yield strength, the yield point, the ultimate tensile strength, the elongation and the reduction of the area at temperatures between 10 degrees Celsius and 35 degrees Celsius. So the purpose of the tension test, in order to know all of these properties, the yield strength, the yield point, the ultimate strength, the elongation, and the reduction of the area at the temperatures between 10 degrees Celsius and 35 degrees Celsius. So the test should be done between those temperatures. We have several cross sections. Shapes are permitted, such as round and rectangular. So you could use many type of the specimen. Mainly, the most used one is the round cross section. Then we need to place the steel bar into this machine, the tension machine, and then we need to attach a recorder in order to determine the elongation, and also we need to have something in order to record the load. We need to have cell load in order to record the load, and also we need to have maybe LVDT in order to determine the elongation. And then all of these values should be recorded so that you can generate the stress strain diagram. You are going to apply a force up to failure. So after you apply this test, then the stress strain diagram is going to be generated, and you are going to know the proportional limit, the yield point, the ultimate strength, and the rupture. The a linear elastic response is displaced up to the proportional limit. So up to the proportional limit here, we are going to have elastic response. Then as the stress is increased, when we increase the stress beyond the proportional limit, the steel will yield. Yielding, it means that the strain will increase without an increase in stress. So here, the strain is going to increase without any increase in the stress. We call this level or process, we call this yielding. Then after that, as tension increases past the yield point, the strain increases following a nonlinear relation up to the point of failure. So after the yield point here, the behavior is going to be non-linear, while the behavior before the yield point is going to be a linear behavior in general. So also we need to understand the effect of the carbon on the stress strain diagram. So in this graph, the tensile stress strain diagram of hot rolled steel bars with different carbon contents. So here we have conducted many tests with a different percentage of the carbon. So in the first test here, the percentage of the carbon is 0.19%, here is 0.49%, and here is 0.64%, and finally here is 0.9%. So we need to know the effect of the carbon percentage. So different carbon content steel level have different stress strain diagram relations. The stress strain diagram is going to be different. Then increasing the carbon content, if we are going to increase the carbon content in the steel, then the yield stress is going to be increased. So here, if I'm going to increase the carbon percent, then the yield stress is going to increase as well, and the ultimate stress, of course, is going to increase as well. But the ductility is going to be reduced. So you increase the percentage of the carbon, but here the ductility decreased and decreased. So increasing the carbon content from 0.19 from this value to 0.9% to that value, then that is going to increase the yield strength from here, for example, here to 8 megapascal to 620 megapascal here. So the yield strength is going to move from 280 megapascal to 620 megapascal. Okay. Also, this increase in the carbon content decreases the fracture strain from about 0.27 here, 0.27 to 0.09 here. The fracture strain is going to decrease. But you need to understand this, even though we have all of these changes, the value of the modulus elasticity is going to be the same. So here, if you measure the slope here, which is the modulus of elasticity, is going to be the same for the different type of the carbon. You need to remember this. Also, we have the torsion test. Also, we have done that test here. The torsion test should be conducted according to ASTM EU143, and this one is used to determine the shear modulus of structural element. We know that the shear modulus is important, especially in the members subjected to torsion, such as rotating shafts in the cars and into automobiles and so on. And in this test, a cylindrical or tubular specimen is loaded either incrementally or continually by applying external torque. So we are going to place the specimen here, and we are going to apply external torque in order to cause uniform twist within the gauge length. Within this length, we are going to cause uniform twist. And you are going to apply the torque, and also you are going to get angle of twist. So you need to measure the torque and the angle of twist so that you can generate the shear strain. And then if you come up, or if you manage to generate the stress, the shear stress and the shear strain, then you will be able to do modulus, which is the ratio of the maximum shear stress to the corresponding shear strain below the proportional limit of the material. So if you measure the slope of that line, then you are going to determine the shear modulus. Finally, we have the bend testing. The bend testing is important because usually we are going to bend the steel. So also we need to know the ability of the steel to resist cracking during bending. So the bend testing is the ability of the steel or a weld to resist cracking during bending. We are going to bend the specimen through a certain angle and to a certain inside radius. So here we are going to put those rollers here. We are going to apply a force so that we know that how much we can bend the steel. And this one is important because steel is often bent to a desired shape, especially the rebars. Also, it's very important test, and usually we are going to do this in the site to make sure that we can bend the steel without any problem. So I'm going to stop here. If you have any questions regarding this, please ask me.